everyone. This recording is for Module 10 in physics, and this module is on periodic motion. And periodic motion is simply motion that repeats itself regularly. So some examples of periodic motion would be anything moving in a circle. So we've already studied uniform circular motion. That would be an example of periodic motion. The beating of your heart is an example of periodic motion. When the windshield wipers are on in a car, that also is an example of periodic motion. And your book also mentions pendulums as an example of periodic motion. So in discussing periodic motion, we need to address Hooke's law. Hooke was an English scientist in the late 1600s, and he did a number of things, but we're going to specifically focus on his work with springs. And if we have a spring that is suspended, so this is a spring. If we have the spring, and they should be identical, I didn't draw them exactly, but if we have two springs and we suspend a mass from one of these springs and we suspend a larger mass, so I don't know, we can say this is 2 kilograms mass and this is a 5 kilogram mass. If we suspend these masses from the springs, what we would see then is what is the relationship between the length of the spring and the mass that is applied to the spring. And if we, so when a mass or weight is applied to the spring, it's going to stretch the spring. And so then we want to know how does the length of the spring relate to the mass of the object, or the mass of the object being suspended from it. So if we were to plot, and this is an experiment that we will do later. I'm sorry we aren't able to do it now, but if we were to plot the weight in newtons, and of course you know that you can get the weight by multiplying the mass times gravity, and then if we plot the weight of the object that was attached to the spring in newtons on the y-axis, and on the x-axis if we put the length of the spring in meters, what we would see is that we would see a pretty linear relationship. In other words, as the weight of the mass, as the weight of the object that is suspended from the spring increases, the length of the spring also increases. So we would say that it's a linear relationship, and that the weight of the object and the length of the spring are directly proportional to each other. As one increases, the other increases. Using experiments similar to this, Hooke was able to come up with a formula that says that force is equal to negative K times delta X. So as you add weight to our spring, so let's start again here. So we have a spring. As we add weight to that spring, the spring will stretch. And the force, as that spring is stretched, the spring will pull up on this weight with a force that is equal to the pull of gravity. Okay, so the weight pulls down on the spring, and then the spring will pull up with a force that is equal to the pull of gravity. If it didn't, the weight would not be able to stay suspended. So the force that is applied is directly proportional to the stretch of the spring, or the distance that the spring is stretched. So force increases linearly to the stretch of the spring. Okay, so then we also, let's look at the signs. So if you pull down on the spring, so pull down on the spring, then the spring will pull upward. Pull down on the spring will pull upward. If we were to compress this spring, so if we had the spring and we compressed the spring by pushing up on it, then the spring would push downward. Okay, so the force is always applied in the opposite direction to the displacement. Okay, so let me write that up here. So the force is applied opposite the direction of the displacement. Force is applied opposite the direction of the displacement. So that's just what I said earlier, is that if you pull down, then the force will be applied up. If you push up on the spring, then the spring will apply a force downward. So there is an optimal length that a spring will try to attain, and it'll try to stay at that length. And if you stretch the spring or if you compress it, it's going to try to get back to that optimal length. And how's it going to do that? Well, it's going to do that by supplying a force in the opposite direction. So the optimal length we call the equilibrium position. So this is when this is the length or the position of an object when there's no force acting on it. And then the other word then we use is the restoring force. And that is the force that is applied to try to bring it back to an equilibrium position. Okay, so the F in this equation is the restoring force. It is the force that is applied to bring the spring back to its equilibrium position. So if there's no forces being applied to the spring, it will stay in its equilibrium position. But if you stretch or compress the spring, then a restoring force will be applied that is opposite the displacement. And the purpose of the restoring force is to get it back to the equilibrium position. And as we've already said, the restoring force is directly proportional to the distance that the spring is displaced. Okay, we don't have time to get into all of this, but so let's look at our equation again. So force is equal to negative K times delta X. So F will always be in the opposite direction as the delta X. So then we ask, what is K? Well, K is a constant. And let me very quickly, I'm not going to ask you really to reproduce this, but just to show you. So you probably remember from algebra that y is equal to mx plus b, and m is the slope of the line. Okay, so this is the and also b is the y-intercept. Okay. So if the y-intercept is 0, so we can get rid of this. So y-intercept is 0, then what we are left with is that y is equal to mx. And that looks an awful lot like f is equal to k times x. That's times delta x. So all of that to show you that in this equation, k is the slope of the line. So it's the change in y over the change in x. Well, what does that tell us? Does that tell us anything? Well, it does, and what it tells us And the reason K is important is that K, which is the slope of the line, tells us about the strength of the spring. So if you have a small k, that means that it's easy to stretch, or it's easy to compress. So in other words, if you think about a spring, if you can easily stretch it or compress it, it's a weak spring. And then conversely, if you have a large K, then that means that it's hard to stretch or compress it. So in other words, it is a strong spring. So all K gives us then is a measure of the strength of the spring. Okay, so let's look at example 10.1 in your book, which is on page 322. And in this problem, we have a spring and the spring the spring hangs down to a certain point, but then when we apply a weight to it, the spring gets displaced, and the distance between here and here is 2.51 centimeters. So this is, let me make this a little more apparent. Okay, so when we hang a weight onto here, so here's our weight, the displacement, the distance between here and here is 2.51 centimeters. Okay, so then we want to know if this object is 451 kilograms, then what is the spring constant? Okay, so let's put up our equation. F is equal to negative K times delta X. Okay, so we know that delta X is 2.51 centimeters, but we typically use our units in meters, so we're going to put that in as 251 meters. Okay, so then let's look at force. Well, what is force? The force of gravity is being, so this object has a force of gravity, so we know that the weight is what will, the force of gravity is what will determine the object's weight. So we can say that the weight is equal to 451 kilograms times 9.8 meters per second squared. So the weight is equal to 4.4 times 10 cubed newtons. Okay, now here's an important point. the force of gravity is downward, right? It's pulling downward, and so this weight would be negative. Okay, so then what does that tell us about the restoring force? Remember that the restoring force is always opposite the direction of the displacement, and that displacement is due to the force of gravity. So the restoring force is going to be positive, and it will, as we said, it's directly proportional to the force of gravity. So it's going to pull in the opposite direction, and it's going to be equal to 4.4 times 10 cubed newtons. Okay, so now we can look at our equation again. Now we know the force and we know the displacement, so we can determine K. So the restoring force F is 4.4 times 10 cubed newtons. And if we divide that by 0.251 centimeters, that's going to give us K. Okay, and the displacement is negative. That'll actually give us negative K, because the displacement is going to be negative, so that's going to give us negative K. So if we do this math, what we end up with is that the K is equal to 1.8 times 10 to the fifth, and the units for K are newtons over meters. Okay, so how many newtons does it take to displace it per meter? And this may not mean anything to you. This number may not mean anything to you, but as you compare the K in other problems, you'll see that this is a pretty strong spring. Okay, so that is example 10.1. Let's go ahead and do on your own 10.1. And that is on page 323. So in this problem, we are told that a student hangs a 25.0 gram object on a spring, and it stretches down 3.45 centimeters from its equilibrium position. What is the spring constant of the spring? Okay, so let's convert this to kilograms, and let's convert this to meters. And then we know that the object will be pulling down with the force of gravity, which is weight. So weight is equal to mass times gravity, so 0.025 kilograms times 9.8 meters per second squared, and that'll be negative because the gravity is pulling down. So the weight of the object will be 0.245 kilogram meters over second squared, or newtons, and that'll be negative. Well, then that tells us then that the restoring force will be a positive force in the opposite direction, so it will be 0.245 newtons. Okay, so now we have everything that we need to be able to calculate the strength of the spring, or K. So we know that F is equal to negative k times the displacement. So F divided by delta x will give us negative k. Okay, so the restoring force we just said was 0.245 newtons. And delta x will be in the negative direction because that weight is going to stretch the spring downward, and we usually define downward as negative. So delta x will be negative 0.0345 meters. So if we do this math, that's going to equal negative k, and therefore k will be equal to 7.1 newtons over meters. That will be equal to k. So if you compare that value to the value for k that we got in the example problem we did, it was 1.8 times 10 to the 5th newtons over meters. So this is a much weaker spring compared to the spring that we saw in the previous example problem. Okay, so that is on your own 10.1. Let's go ahead and do on your own 10.2, just to keep giving us a little more practice on these. So 10.2 tells us that a physicist hangs a 412-gram object, and we're told the spring constant is 11.91 newtons over meters. And now we are asked, how far will the spring stretch? Okay, so same equation, we're just going to solve for something different. So let's go ahead and change this to kilograms. So it'd be 4.412 kilograms. And we know that the object will be pulled down with the force of gravity, and therefore we can that is the weight. So we can take the mass, 0.412 kilograms, and multiply that times gravity, so that we get the weight is equal, and this would be negative because gravity is going to be pulling downward. So we get 4.04 newtons. Actually, probably 4.1. No, 4.0 newtons, and that will be negative. So then we know that the restoring force, F, will be the same value in a positive direction, because that's the force that will be applied to try to get that spring back to its equilibrium position. So we'll go back to our equation. F is equal to negative k times delta x. So F divided by k will give us negative delta x let's see, let's just divide by negative k, I guess. Let's just divide this by negative k. So 4.0 newtons divided by 11.91 newtons over meters. So your newtons are going to cancel. and you'll get that delta x is equal to negative 0.34 meters. So this negative indicates that the spring will be stretched downward. So it's a negative displacement, a negative delta x. Okay, so gravity is going to pull downward, and the restoring force then will pull upward with an equal force as that caused by gravity in order to try to get that spring back to its equilibrium position. Okay, so there are some problems in the back of the chapter that you can work just to get some more practice with figuring out K and figuring out displacements and forces. We're going to go ahead and go on to the next section. In order to do that, I'm going to take you through some derivation of equations, but the one thing I want to emphasize is I'm not going to ask you to reproduce these derivations, and if you don't understand them, it's okay, but I do think it's important for you to see how we get there. If you're interested in it more, if you have more interest in it, you can certainly look at the book and try to follow and understand those derivations, but just keep in mind that we are going to do some derivations, but at the end of it, I will tell you what formulas are important for you to know. Okay, so before we jump in, let me briefly explain an experiment that you will do later, but it's important for you to understand what would happen. So in this experiment, we're going to have a spring, and you're going to have a mass hanging from that spring, and it doesn't really matter I think your book has you use a mass that's 200 grams, but that doesn't really matter too much. It doesn't matter at all, really. And then what you would do in this experiment is that you would pull the spring down at different increments. So first of all, you would pull it down 5 centimeters and then let it go. And when you let it go, what you're measuring is what is the amount of time that it takes for this mass to go up and down a certain number of times. Okay, so you're going to pull it down 5 centimeters, let it fly, and then let it go up and down 5 times and record the time necessary for that to happen. Okay, then you'll do the same thing, but now instead of pulling it down 5 centimeters, you're going to pull it down twice as far. And again, you're going to let it fly, and you're going to measure the time that it takes to go up and down 5 times. Then same thing again, but you're going to pull it down even farther. So let's say we go down 15 centimeters, and you're going to let it fly and see how much time does it take to go up and down, up and down, up and down 5 times. Okay, so that is what experiment 10.2 does, and let's talk about what you would see from that experiment. Okay, first of all, if you think about it, when you have this spring and you have a mass that is hanging from that spring, we call this a mass spring system. Okay, so when you pull this thing down and let it fly, it's going to go down and up and down and up and down and up. So therefore this experiment is an example of periodic motion, because the bag is going to, the weight that you attached it's a motion that's going to be repeating itself regularly. So it is an example of periodic motion. So what other things would you notice about this, the movement of the mass? Well, what the big idea that you would notice is that no matter how far you pull it down, the time did not change. So the amount of time that it took to go up and down, up and down, up and down 5 times, it didn't change. So it didn't matter whether, it won't matter whether you pull this thing down 5 centimeters, or whether you pull it down 10, or whether you pull it down 20. The amount of time that it takes to go up and down, up and down, up and down 5 times is not going to change. And if you remember from our previous discussions, the term that we have used for time is period. And we've designated that with the letter T. So what this tells us is that the period is independent of how far you pulled it down. And you think, how can that be? Well, the reason that can be is that, and then another thing I should mention is that if you release it, so if you pull it down if you pull it down to 10 centimeters, it will never go more than 10 centimeters above or below. So if we have our spring and we have a mass attached to it, and if I pull this down 10 centimeters, when I release it, it's never going to go more than 10 centimeters from the equilibrium position. So if this is equilibrium position, if I pull it down 10 centimeters, it's never going to go up more than 10 centimeters. So the distance that it travels from equilibrium is called the amplitude. So if I pull it down 10 centimeters, that's the amplitude. And then it will travel up. It will just be displaced from the equilibrium position in an upward direction 10 centimeters. That is called the amplitude. So the maximum distance that an object gets from its equilibrium position when it's traveling in periodic motion is called the amplitude. So if you release it at 20 centimeters, then the amplitude would be 20 centimeters. So we have a term that we use to describe something in which the period doesn't depend on the amplitude, and that term that we use is simple harmonic motion. So this is just in simple harmonic motion, the period, or T, does not depend on the amplitude. So it's independent of the amplitude. Well, how can that be? The how it can be relates to how the movement relates to the movement of the weight as it goes through its motion. So when you pull that mass down, okay, so when I pull it down, say let's just say I'm going to pull it down 5 centimeters. When I pull it down, it's going to start at a velocity of 0, right? But then when I let it go, it's going to start slowly. And then it's going to speed up. And when it then it's going to pass through its equilibrium point. So it's going to pass through this point where it is in a resting condition. And when it passes the equilibrium point, that's when it's going to reach its maximum speed or maximum velocity. And then what's going to happen? Once it's passed through the maximum velocity, then it's going to start slowing down again. And when this gets back up to 5 centimeters up here, when the displacement of this weight gets back up to 5 centimeters, then its velocity is going to be 0. And then it's going to start moving in the opposite direction, and the process will start all over again. So it will start slowly from up here. It'll speed up, and when it reaches the equilibrium point, it will be at its maximum velocity, and then it's going to slow down until it reaches this point here again, and in which its velocity will be equal to 0. So we could summarize that. Your book summarizes it by saying this. So the highest acceleration is at amplitude. So it's speeding up or slowing down at the amplitude. The highest speed or velocity is at equilibrium. At equilibrium, acceleration is 0. And at amplitude, the velocity is 0. Okay, so maybe write those down and just you could draw yourself some drawings and think about um, how that is true. So if we have a mass spring system, here's our mass, and we're going to pull that mass down and we're going to release it. So it's going to have its highest acceleration. It's going to have zero velocity here, and it will have zero velocity at the other end. But when it's at its amplitude, it's going to have its highest acceleration. And then when it reaches equilibrium, when it's back to its normal resting state, then it's going to have its highest velocity, but it will have no acceleration. And then again, when it reaches its amplitude on either end, then the velocity will be equal to 0. So that is just an example of that's an explanation of what you see in a mass spring system. So let's I'm going to show you some derivations now and really just end up with one equation that you need to know. Okay, so you know that if we're talking about something going around in a circle, so here's an object, it's going to travel around a circle. You know that velocity is equal to distance divided by time, right? How far does it travel in what time period? That's what velocity is. Well, when we're talking about going in a circle, what is distance? Well, distance is circumference, right? So that's 2 pi r divided by time. Okay, well then you also know that centripetal acceleration is equal to v squared divided by r. Okay, so now what I'm going to do is I'm going to substitute this v squared, I'm going to substitute for this and square it. So then what you would have is that centripetal acceleration is equal to 2 pi r over t, and we'll square that whole thing. Okay, so all I did here was just these v squareds, I just replaced it with this. Okay, because we said that is what v equals to. So then that if we go ahead and square this whole thing, then we end up with it. So centripetal acceleration is equal to 4 pi squared r divided by t squared. Okay, because this r will cancel when we square that whole thing. Okay, so then if we we can use this equation to a mass spring system, but we can't use radius because we're not moving in a circle. But this equation does define a mass spring system if we replace radius with amplitude. Now, in order to do this, you have to understand that a mass spring system is basically a one-dimensional equivalent of something moving in a circle, uniform circular motion. And we don't have time to go into it, but your book presents a description of how you can see how that would be if you think about something in a circle, moving in a circle, and the shadow that it depicts. So the key here is that the mass spring system is one-dimensional motion. It's like uniform circular motion, but it's in a single dimension instead of two-dimensional. So we can use this equation for acceleration by replacing the radius that we used in uniform circular motion by replacing the amplitude if we're talking about a mass spring system. Okay, so then what do we have then? What we have is that centripetal acceleration is equal to 4 pi r times the amplitude divided by t squared. Well, previously we have seen that for a mass spring system, force is equal to negative k delta x, and we can replace this delta x with a, so then we have negative k times a, and what is force? Well, you also know that force is equal to mass times acceleration. So if we rearrange all this, what we get is that the acceleration is equal to k times a times the amplitude divided by m. Okay, so then this we've already said, so this is acceleration. So now let's set this equal to that, because this also is acceleration. Okay, so if we do that, and then if we solve for t, what we end up with is that t is equal to 2 times pi times the square root of the mass divided by k. So even if you didn't understand how we got there, this equation is really important, and what it tells us is that period, so t, period is only dependent on 2 things. And what is that? The period is only dependent on the mass of the object and the strength of the spring. And that's what we showed, we talked about previously, is that if you have a spring and you have a mass on it, and you pull this thing down 5 centimeters or 10 centimeters or 20 centimeters, the period with which this spring will go up and down does not depend on the amplitude. It doesn't depend on how far you pull it down. It depends only on the mass and the strength of the spring. So amplitude does not affect the period. The only thing that affects period is how strong or weak the spring is, and the mass of the object that is being pulled down. Okay, so let's do some problems. Let's just start with a simple one. We'll start with example 10.2, and that's on page 331. So in example 10.2, we have a 345 gram mass and a spring constant of 35 newtons over meters. And we want to know what is the period of the spring's motion. Okay, so we know our equation is that T is equal to 2 pi times the square root of m over k. So T is 2 times pi times the square root of the mass in kilograms, so 0.4345 kilograms divided by 35 Newton over meters. Okay. I'm going to go ahead and put, so a Newton, as you know, I'm going to go ahead and put this in just so we can see units. So a Newton is a kilogram meter over second squared. So I'm going to make sure that you know that this whole thing is the square root. So kilograms will cancel, meters will cancel. You'll be left with second squared, and we take the square root of that, you're going to get seconds. So T, if you do that math, T is equal to 0.62 seconds. Okay, so the amount of time using a mass of this amount and this strength of the spring, that in simple harmonic motion going up and down, it will take 0.62 seconds for that mass to go from its amplitude up and back down. 0.62 seconds. Okay, let us go ahead then and do let's do the on your owns, and then I think we'll be done for this video. Let's do on your own 10.3. So this one says we have 11.2 kilogram mass, and in this case we're told the period. So T is equal to 2.3 seconds. What is K? Okay, so for this one, we know that T is equal to 2 times pi times the square root of m over k. So if we plug in what we know, then put our time in here, equals 2 times pi times the mass, which is 11.2 kilograms, divided by k. Okay, so then let's, to get rid of these square roots, we're going to square everything. So it would be 2.3 seconds squared equals 4 pi squared times m over k. And the m was 11.2 kilograms divided by k. Okay, so then we can just solve for k. So k is equal to 4 pi squared times 11.2 kilograms, 4 pi, times 11.2 kilograms, divided by 2.3 seconds squared. Square that, and that will give us k. And with significant figures, I get the k is like 83.5. Kilograms over seconds squared, if you do the math. So this is kilograms over seconds squared. So with two significant figures, we would say that that's 84 kilograms over seconds squared. That's kind of an odd unit, right? We haven't seen that before. So let me show you why that's an okay unit. Kilograms over seconds squared. Well, if I just take this Newton and make it kilogram meters over second squared and then put it over meters. So all I did was just write out what a Newton is, kilogram meters over second squared, and put it over meters. Then I can show you how this is then equal to a kilogram over a second squared. So here the meters are going to cancel, right? Because you have one on top and one on bottom. So basically, kilogram second squared is the same as a Newton over a meter. Okay, so you can write this answer as a kilogram over second squared, or you can write it as 84 newtons over meters. Okay, let's go ahead and do the on your own 10.4. And in this problem, we have a 351 gram mass, and a certain spring stretches 12.1 centimeters. If the mass is pulled down 5.1 centimeters, and then it's released, then what will be the period? So again, here's the situation we have. We have a spring, and we have a mass hanging from that. And when this happens, the displacement is 12.1 centimeters, but then we're going to pull this thing down 5.1 centimeters from its equilibrium position. We're going to let it go. And we want to know, what will the time be? Okay. So the first thing you have to realize about this problem is that when it talks about pulling it down 5.1 centimeters, what is that? That's the amplitude, right? And we know that period does not depend on amplitude, so we do not need to know that information. Okay, so, but this equation does, it does require us to figure out some other information, because we know that T, we don't need to know the amplitude. We know that T is equal to 2 times pi times the square root of m over k. So we know m, but we don't know k. But we can get k, right? Because we know that F is equal to negative k delta x. And we know that this F is going to be the opposite of the weight, the opposite sign of the weight. So weight is equal to mass times gravity. So that's going to be 0.351 kilograms times 9.8 meters per second squared. So weight is going to be equal to negative 3.4 newtons. And we know that the restoring force is in the opposite direction of the force of gravity. So F is going to be 3.4 newtons. And the displacement is going to be 12.1 centimeters, or 0.121 meters. And it's going to be in a downward direction, because the spring is going to pull down on it. And so that's going to give us k, negative k, which will give us k. All we have to do is change the sign and we get k. So k is equal to 28.1 newtons over meters. That is equal to k. Okay, so now we have what we need to determine the period. So we had to first solve for k by getting the weight and using this equation that we had seen for that we'd used for periodic motion. Once we have k, then we can plug that into our equation for to determine the period. So T is equal to 2 times pi times the square root of the mass, 0.351 kilograms, divided by 28.1 kilogram meters per second squared over meters. Okay, so meters will cancel, kilograms will cancel. We're going to take the square root of second squared to get seconds. So T, if we do all that math, T will be equal to 0.70 seconds. Okay, so the time required for this spring, we have a weight or a mass attached to here. We're gonna pull this down 5.1 centimeters, and we're gonna let it fly. How long will it take to go up and back down? And the answer is that it will take 7/10 of 1 second. Okay, then let's look at 10.5, because 10.5 says if instead of pulling it down 5.1 centimeters, what if we pulled it down 10.2 centimeters? Then what would the period be? Well, the answer is that the period is going to be the same, because remember, this is a measure of amplitude, and period is only dependent on mass and the spring constant. It's not dependent on amplitude. So the answer to 10.5 is also 0.70 seconds. Okay, I think we are going to stop there. That's enough for today. We'll pick up and finish up the rest of the chapter next week. And then we'll also work some of the practice problems at the end of the module next week.